Hello, this is Derek Dean, and I, along with Hugo Castro, will be performing the webinar for the ETAP 21 release, Part 2. During this webinar, we will be discussing a number of our products, from the monitoring, control, training, and situational intelligence, to advanced protection, automation, analysis, and asset management, to the digital twin-driven automation and renewable energy power management solutions. I'd like to start by discussing the eWeb product, which is an infrastructure which supports the web-based SCADA solution. eWeb is a single platform which allows users to visualize, manage, and integrate many different applications within the ETAP suite of products using a standard web browser. Some of the key features include a combined solution for many different applications, a common set of HMIs between the SCADA HMI and web HMI, and ETAP analysis over the web. There's built-in role-based authorization with integration with Windows Active Directory and Gmail, a cohesive, complete user profile management solution, so every time you log in, you have the exact same custom environment. With the web HMI, we typically start with the ETAP digital twin, which is used for planning and analysis purposes. We can automatically generate your SCADA HMIs from that model, and those same HMIs can be visualized using our HMI Viewer, which is our thin client for operations, as well as through eWeb. So it's one common single source of truth. Here are some of the products which are leveraging the eWeb interface, from SCADA to OMS to analysis and advanced applications. Now I'd like to go through a quick demo of the software in action. Here you can see the standard ETAP product, which is used for planning and analysis. Here you can see all of our studies that we can run against this electrical model. And this is typically the starting point for our web applications. So the first step is to take this system online. So adding metering points, adding any other electrical equipment that you need, and then you can do your mapping and set the system to go online. So here my system is online. Everything in this orangish color is real-time data, and everything in red here is my state and load estimation data. Now from here, we can export this into our HMI designer. So here is our HMI designer. This is of substation number 1. So if I go back to ETAP and go to substation number 1, you should see that this page here looks very similar to this page in the HMI designer. That's because it was used to create this page. That means all of your HMI pages are automatically created. And here you can add and remove all sorts of components, gauges, trends, etc. into this page to make it more user-friendly. Now once you save this and deploy it, now it's available through my HMI Viewer. So here's my HMI Viewer, which is my thin client for operation, which is simplified for your operators. Now what we've done is we're reading the exact same HMIs that we're using here in our web user interface. So here is our main overview page, which should match that first page I showed you in ETAP. And if I jump into substation number 1, here is our substation number 1 page, which looks exactly the same as our thin client. You'll see here, this is our thin client. It's exactly the same. It's using the exact same database. Here you can see all of your real-time data updating in real time, any operator notes or service tags, if you have any trends or gauges. You can also operate from this screen if that's something that you're interested in doing, but it is possible to disable this functionality as well. It's template-based, and we support pop-ups and other dialogues. So if you want to make your data a little bit more robust. Now if I move to the top here, I have my navigation bar, which has many different options. This is part of a suite of solutions. So I'm just going to go through a couple of these very quickly. So I showed you my main overview and my navigation to different HMIs, as well as my, I can show my alarms here. So here I have one alarm in the system. One thing that's very nice is when you have an alarm, and if it generates an email or an SMS, we automatically can add a link. So then you can click that link and jump to this page and actually jump right to here, so you can, from your phone, very easily acknowledge the alarm or delete the alarm or view all alarms. So you have one very easy way of seeing what's happening in the system. Additionally, we have events and tabular dashboard, which shows you all of the real-time data in the system. We have a trending tool, where here you can see a trend of my real-time data. So here's bringing in my historical data and then all of my real-time data as it updates. We support lines, bars, bars with a quality analysis, pie charts. We have a number of different ways of showing this, as well as bringing in your raw values only, alarm bands, your minimums, your maximums. So we can perform some analytics on this data as well. Here we have a one-line view. So this is your electrical model as defined in ETAP, and you can perform studies. So for instance, you can run unbalanced load flow with what if analysis and say what would happen if I were to open this breaker or close this breaker, and it will actually run your load flows and show the results here. We have eProtect, which will be discussed in a separate section. Situational Intelligence, which will also be discussed in a separate section. Reporting, where you can view and create on-demand reports. So for instance, here I'm going to pull up a scheduled report. Advanced fault analysis software, our asset management tool. For an OMS solution, all of your customer information can be stored here. Your crew management, where you can create your crews, add employees, and have all of your shifts defined. We do have a calendar feature where you can see all of your scheduled tasks. And we have a configuration tool here where you can customize what applications you can see up here. So for instance, here I have my SCADA HMI, and these are my pages here, but then I can go and customize this. I can add a new link and say show my overview 2 page, and then I can go to that page here, and then I can customize it. I can say maybe edit my layout and have multiple pages displayed here. And then in each of these HMIs, I can have a separate view. So for instance, here I can show substation 1, and here I can show substation 2. So this really allows your end user to get a wealth of information in one page. Next, I'd like to discuss the eOTS product, which is the Operator Training Simulator. This is a model-driven operator training simulator, which means that we leverage the intelligence of the ETAP analysis and planning tools to provide a realistic and cohesive simulation solution against the same user interface as the operation environment. Some of the key features include a realistic response to actions taken by the operators. This is because it is a model-based solution, so you actually get that system response, not just seeing if the circuit breaker is opened or closed. We have simulation of predefined scenarios based on actual operational events that happened in the past, but also support ad hoc trainer actions. So ad hoc, a trainer can go and inject an event or a trip signal during an actual training session. Trainer tools are used for trainee evaluation, both in runtime as well as after the fact with reports and playback studies. Additionally, this can be used to validate updates to the electrical system before commissioning. So if you're bringing on a large addition to the electrical network, you can validate that using the OTS and make sure that both the system can handle this, as well as the operators are ready to hit the ground running once this equipment is commissioned. Some other major key features are the support of the system dynamics. So for instance, the inrushes involved with starting up very large motors or ramping up and down generators. Relay protection schemes. So we take into account if relays are modeled in the electrical model, digital twin, we can automatically trip breakers based off of overcurrent, under frequency, etc. And then controller logic. So for instance, if you have a microgrid controller, a PPC, or any other sort of controller, we can take that logic into account and use that to update the response to the system. At its heart, what we do is we transform the production SCADA to an OTS environment. So here you can see a typical production environment where your RTUs, IIDs, relays are communicating through some industrial protocols to your production SCADA. Here we replace the IIDs in the field with the eOTS simulator. Then using standard industrial protocols, the eOTS SCADA environment can capture that data from the simulator. For this solution, it's possible to have both a standalone training environment where each trainee has their own separate simulation, or you can do team-based training where you have multiple individuals which are connected to the same simulator and can affect one another's work. Next, I'd like to give you a quick demo of the eOTS in action. Here we can see the same user interface used for production. However, this is in a simulation environment used for training and testing purposes only. I will start by opening this CB here, just like in production. However, instead of sending the signal to the device in the field, it is sent to the digital twin, which is providing a real-time response. Additionally, I'll open the isolator switch here. See how the response is updated. Next, I will demonstrate how the digital twin provides a complete system response. In this case, the power is flowing from the utility into the bus 1 and then being sent to the adjacent substation. If I open the circuit breaker, you will see how the flows coming from the utility are affected, going to 1.16. Next, I will close the bus tie circuit breaker, and again, we will see how all of the flows in the system are affected. You can see how flows are going from that circuit breaker on the utility side through the bus up to the other outgoing substation. Here is the ETAP digital twin, which is the intelligence behind this solution. This tool can be used for planning and analysis purposes as well as the OTS. Here we model all the connectivity as well as critical electrical parameters, including the ratings and impedances, etc. Using the study case editor, users can create scenarios for simulation. For example, in this scenario we have design loading, and we've created a scenario where this circuit breaker, CB11, trips after 30 seconds. There's no limit to the number of actions that can be performed, so you can create a cascading effect. Here you can see the trainer tools which are used to manage a training session. In this case, we are connected to trainee number 1. In this page, users can see all scenarios and execute them for the trainees. Here I am initiating the normal loading session with no events. Within the trainer tool, trainers can visualize the same HMIs as seen here, but also perform advanced actions on the system. For instance, here I am sending a trip signal for this circuit breaker. And I'm sending it to trainee number 1. Note that the diagram is automatically updated here, and when I navigate to the power operation environment, you can see that it is also updated. Then if I go ahead and open another CB from the trainees environment, here we can see in the trainers environment that the system is updated as well. The ETAP eOTS solution also provides a playback facility to review in a step-by-step fashion all of the actions that were performed. Here I am selecting the trainee which I would like to review, and now you can see all of the snapshots are recorded. Once I select a snapshot, using the right toolbar, trainers can walk forward and backward through time and see all of the flows in the system. So you can see when the circuit breakers are open and closed, and you can see the actual flows in the system. Next, I'd like to discuss the ESI Situational Intelligence product. ESI is the intelligence behind your SCADA solution. Whether a greenfield implementation or a brownfield existing solution, ESI can take your conventional SCADA to the next level, offering information just not available in the industry today. First, ESI predictably identifies problem areas before the operator takes a given action. This gives you the confidence to take actions because we've already run these actions and know how the system will behave. Additionally, ESI can provide unique insights about your system, highlighting problem equipment and areas of the network which could benefit from maintenance or upgrades. Lastly, this solution is equipped to integrate with virtually any SCADA solution in the industry today. The heart of the ESI product is the ETAP digital twin, which is the digital representation of the electrical equipment in the field. Then we leverage the mature state and load estimation and predictive simulation products. We take the solution to the next level by predefining common scenarios and running these scenarios periodically to proactively identify how the system would behave if certain events or actions occur. Finally, the configuration and results are available in a web user interface so users can easily visualize how the system would behave. Now I'd like to give you a brief demo of the product. Here we can see the ETAP electrical model, which we've configured for real time, where we've added meters in the locations needed. We bring the system online, and we have our state and load estimation calculating along with our real-time data from the field. Here we can see some SLE alarms, state and load estimation alarms. So these are alarms that wouldn't otherwise be available in a SCADA system utilizing the actual state and load estimation data. Next, I will go to simulator mode and create a scenario. I've predefined a scenario here where I isolate transformer T47, and here you can see a number of other scenarios as well. Here is a scenario where I'm tripping my PP4 power plant number 4. Now I go to my web view in eWeb, and I can add these scenarios to be run periodically. Here they're running every 3 minutes against real-time data. Now when I navigate to my alerts section, you can see which scenarios will lead to alerts. So for instance here, the isolation of T47 has no alerts, but if I start up the large crusher, I will have critical alerts. And here if I isolate T67, I will have marginal alerts. With this information, it is clear to the operator that they should not perform certain actions without first consulting an engineer to make sure that the system is going to behave correctly. Next, I'd like to discuss the eProtect product, which is a centralized relay management system. At its heart, eProtect is a relay management system with automated setting extraction, parsing, and processing, but there is much more. It's an integrated interdivision IT supported environment with workflow management built in, implementation of a controlled and transparent multi-stage setting workflow process. There's an optimized data flow, which allows the control of the setting by tracking the origin of the settings values for each parameter. And there's integration of the relevant email communications within the same setting management database system. This is a web-based solution, which means there is a main eProtect real-time server in the backend and a web server, which can be on that same machine, and then a web browser, desktop clients, mobile clients, tablets, anything else, as long as they have access to that web server, can have access to eProtect. Here we can see how eProtect fits into the entire solution, where you have the protection relays, which are communicating to the design and analysis workstations where you're running protection coordination studies. And you have your eProtect web clients, where you can visualize and see and extract the settings from the relays themselves. eProtect has, as I mentioned before, a robust settings workflow, which is all managed through our switch order management solution, where the settings can be extracted, imported into eProtect, sent to ETAP, validated, then updated once you've validated and updated the settings, updated back to eProtect, and then you can export those settings back to the relay. Next, I'd like to discuss the EAPM, which is the Integrated Asset and Maintenance Management Platform. Some of the features for the eAPM is on the asset side, where you can visualize all or some of your assets in your ETAP model. You can have multiple projects supported in one instance, and you can bring in other elements that don't exist in the ETAP model, so non-electrical assets. So you can bring those into your asset management platform. You can manage, so everything is through a same web UI. There's user access management built into it, and there's custom filtering and sorting for any information that you want to see, and it is all saved to your own user profile. Properties, you can bring in ETAP properties, so for instance your nominal voltages, your ampacity, all of that information that's stored in ETAP model, you can bring into asset management and visualize on the web. But you can also bring in custom properties. Let's say the owner of the asset, or the location of the asset, or an email address, or a phone number, or or serial number. All that information can be brought in and centralized in your asset management tool. You can also bring in attachments. So for instance, cut sheets or data sheets or test documentation, even images, all of that can be brought in and then downloaded from your tablet or uploaded from a tablet so you can download it later on when you're back on site. And on the maintenance side, you can schedule and close work orders, and there is an integration with our switch order management solution. Here we can see how it is synchronized with the ETAP model using the NetPM technology. So you have one or more ETAP models which can be synchronized to our asset database where everything is accessible through the web user interface. Next, I'll discuss the ETAP AFAS Advanced Fault Analysis software. Some of the rationale for the ETAP AFAS solution is that relays and control devices are more accessible remotely than they ever have been in the past. Automated and integrated solutions required to investigate events. Integration of inverter-based sources introduces new system behaviors. Model verification and system simulation has gained significant importance in the fields today. The AFAS solution has a number of functions which give you a cohesive view of what event happened. So first at its heart, the disturbances must be recorded. So these are ComTrade files which are downloaded from the relays or fault recorders. These ComTrade files are extracted and grouped together. The extraction is done through our own or third-party drivers which use FTP, SFTP, IEC 60150, IEC 104, etc. And you can download the events as they happen or on a poll base. Then these are grouped together using time and the electrical model. So if you have two incidents that are separated from another that have a similar time, we know that those are two separate incidents. However, if you have two ComTrade files that are received at around the same time in the same area of the network, we know to group those automatically because we have a model-based solution. Notifications are built in, so emails are sent out, SMS is sent out to indicate what has happened, that we've generated an incident. Waveform visualization is a key piece to any AFAS solution because if you want to go into advanced analysis and really see what happened, you need to visualize those waveforms. We have disturbance record analysis, where we analyze the disturbance records themselves, these waveforms, and then find critical information that might be helpful. So for instance, fault severity analysis, the relay details, the field sequence of operations, what actually tripped and what other trip signals were received. Then we have model-based calculations. We take the information from our disturbance record analysis and apply it to the electrical model, that digital twin, and calculate the fault location or the line impedances. And then we have model validation, where we take what happened and then after the fact we can validate the model, where we can look at the sequence of operations. We can look at what actually should have tripped versus what did trip in the field. And then we can also run a signal injection, where we can play back the fault location and then look at the waveform file that would be generated and see how that matches up with the actual waveform file that was produced. All these applications all work together for the life cycle of your relays. So here we have your as design settings, which is done through the ETAP digital twin running star and star Z for your protection coordination studies. Looking at your as found settings as you extract the settings from the relays themselves and validate that they are accurate and make sense. You have your simulation, your as tested, where you can run your test sets against the relays. You can upload the settings into the eProtect, as well as validate the response using ETAP digital twin studies. Then last, you have your as operated, where your AFAS can download those ComTrade files as an event does happen, and then find all the critical information that you need and give you a very good idea of what happened and how to respond. Now I'd like to give you a quick demo of eProtect, eAPM, and asset management. Here we can see the eProtect Relay Explorer, which is in the eWeb infrastructure. This user interface is available on any standard browser and can be used from a standard PC, laptop, tablet, or mobile device. In the left panel, we can see a list of the classifications. So here I'm filtering on the Angel substation. Here we see a list of the relays associated with that substation. When I navigate to the ETAP model, I can see those same relays there. See here we can see it as the Angel classification, and here are my relays. Now when I select the relay, we can see all the critical information about it and import files. So here I'm going to import a test report to that relay. This is something that has been done in the past, and a PDF file has been created, whether you're testing through a test device or you have your own other procedures for testing. Regardless, we can import as many files as you like, or a zip file to validate and be able to use later on. Additionally, I'm going to import a cut sheet. So this is a relay cut sheet which has been provided from the vendor and can be used for reference later on. So if you're on a tablet and physically at the relay, you can go and download the cut sheet and view that information while on site. Here you can select the download button to download those settings. Now I'm going to import settings from the relay itself. So there's either you can download the settings from the device itself, or you can use the OEM software, the vendor provided software, to download those settings. So here we're using Accelerator to download the settings, and we've exported a file which can be used for import. Now I'm going to hide the classifications and then collapse my relay section so I can focus on the settings. I'm going to show all of my settings, and the first thing you'll notice is there's almost 6,000 settings that have been downloaded and made available for analysis here. So if I go to the ETAP column here, you can filter out only the parameters which are used for analysis by ETAP. So there's a wealth of settings that are provided by the relay, and we use some of those for analysis and we use others just for maintenance and ensuring that everything is there. Now here, when I select the Send to ETAP button, I can see a report of what's changed and then send those using the NetPM infrastructure to the ETAP model. So if I jump to the ETAP model and go to the EProtect Revision, you'll see that the settings in ETAP match those settings that were from the actual relay as found. So here the pickup and time dial should match what we saw in the Relay Explorer. Now I can use either star or star Z to validate my system. Here I'm going to use my star auto evaluation function, and very quickly we'll be able to see if there's any violations. So here I'm expanding my TCC, and I can see for the transformer tab that there is a number of violations. So if I move my curve over and change my settings, then you'll see that there are no longer any violations. I don't have any violations on my load side and no concerning violations on the cable itself. So I'm properly protecting this equipment here. And you can see if I go back to the settings in the properties section, I can see that the settings have been updated. Now when I go to the base revision, which is my as designed revision, I can copy over my eProtect revision settings to my base revision for that relay. And when I do this, I'm automatically pushing those settings, those as designed settings, to eProtect. When I expand my relay section and select my relay, you can see my as designed settings, which were created in ETAP, using ETAP as a tool. And these, additionally, we can check versions. Here we have a version backup of every import that's ever been done. So for instance, here I can compare my settings between two different times and see what's changed. Here my pickup and my time dial have been updated. We can also export to Excel to use later on. So the last step is, now that I have my validated settings, I can export these settings to the vendor file and then import these using Accelerator or PCM600 or whatever. Additionally, we can go to the settings history and see all of the changes that have been made through time. So for instance, here I can see the user and the machine that were used to make those changes. Next, I'll show you the panel layout. So here is a template of a panel layout where I can show the each relay and the real-time data, so my current amperage, my frequency, etc. for each relay. Note that I've only created one template, and this is part of the software for each relay, which can be customized, but you only have to create it once. The health indicator page also shows you critical information for the health of the relay. So for instance, the communication status, the number of trips that they've seen, the number of open and close actions, etc. Next, I'll show you the asset management tool. Here you can see a list of all the equipment in the field. So here I have it filtered just on the 2 winding transformers. You can see the next maintenance, all of the critical information. You can go and schedule new maintenance here. So here I'm going to create a maintenance request for the asset replacement. I'm scheduling it out for a couple weeks from now. I'm setting the duration to 10 hours. And I'm going to include a procedure which needs to be performed for this. And then I can add any comments as I'd like. When I apply this, we update the list here with the next maintenance and also add it to the SOM, switching order management, which I'll show you shortly. Additionally, we can add new parameters. So for instance, if you want to add the primary kV and the secondary kV into the system, now this is the settings that are in the ETAP model itself. But you can also add your own settings parameters for each component as well. So for instance, the owner or the email address, etc. Here I'm going to show you, I'm going to download my next maintenance here, and I'm actually downloading a zip file which has all the information for the maintenance. I can go ahead and close a maintenance request here by just selecting close. I can add my maintenance records as an attachment, and then I can also add comments as well. And here you can see that my last maintenance time has been updated. Here I can select the asset details, and for the selected asset I can see all of the parameters and the history for that asset. So anything that's changed, I can do a comparison of what's changed between versions, and then I can also see what my current settings are. So for instance here, my primary kV and secondary kV weren't updated. Next, when I select the Events tab, I can see all of the events associated with my assets, and I can filter and sort based on my component, my category, what changes were made, etc. When I go to the calendar page, I can see a calendar. So right now I'm showing all my crew shifts, but here I can see all of my switching orders, so all the maintenance that I planned, and when I look in the right panel, I can see all the details for that maintenance. So this gives you a really nice view of what work needs to happen in the near future, and you can plan your week out accordingly. Last, when I go to the switch order management tool, you can see all the switch plans that are created. So for instance, here is my maintenance request that I created earlier for routine maintenance. You can go through and do the review process, create a switch order if one is required, and then you can also go and execute each switch plan. Here I'd like to show you some of the AFAS features. Here's our event viewer where we can see all of the events in the system, including ComTrade events. Now if I double click on one of these events, I'll open up my waveform viewer where I can see the ComTrade files visualized as a waveform. So here we have a number of different features where you can visualize different information about the waveform viewers, including the analogs. Here I have my instantaneous currents, my instantaneous voltages, and also my digitals here, so you can see when the actual circuit breaker tripped. Additionally, we can bring in other information, for instance, RMS values, which are calculated through digital signal processing. Here I'm bringing in my RMS value for my A-phase current here. But we calculate many other values as well, my phasor values, my frequency information, as well as my harmonics, and my power information. We also have user-defined calculations. We can also bring in multiple events at the same time so we can compare, especially if we have multiple ComTrades for one same event. So here I can see from 2 different relays, I'm superimposing the A-phase current against each other. Using the eWeb product, we can navigate to the Afast Viewer and look at an incident. So here we can see the field sequence of events. So for instance, when each digital trip signal was received and what changed. Then we can navigate to the fault location and see the predicted location of the fault, the from bus, to bus, the component that was faulted, as well as multiple different algorithm types that we use to calculate the fault location. Again, we're using multiple different inputs to determine where the fault is located. The relay data is information calculated directly from the relay, including the pre-fault condition, the fault condition, and then after fault condition. Here we can get the voltage and current on the A, B, and C phase, as well as when the information was received. Next, we have the fault severity information, where we can see the fault type, whether it's temporary or permanent. So for instance, if you have reclosers, the fault current and fault voltage, as well as the fault resistance and fault reactance, if that's available. Next in eWeb, we have a waveform viewer, similar to the waveform viewer I showed earlier. Here we can select a ComTrade file and visualize that ComTrade file here. Note that the waveform viewer has a little bit limited functionality from the thick client, but still is a very nice tool for visualizing the fault.
Thank you, Derek. This is Hugo Castro speaking. Now we're going to transition to the controllers part of the webinar. In this part of the webinar, we are going to look at the intelligent controllers. We're going to start with a quick overview, then move to the enhancements in ETAP 21, and last, look at the services that ETAP can provide. Let's start with the power plant control. The power plant controller has primarily two objectives. One is to dispatch generation sources to guarantee performance under operating conditions, and also to, during these conditions, also operate with compliance with local grid codes. In addition, the power plant controller must monitor key components of the plant, but be able to integrate with plant's SCADA HMI and also track key performance indicators to understand how the performance of the plant is. For the microgrid controller, on the other hand, has similar objectives. Now, the first thing to remember is that microgrid controllers, first of all, deal with distributed energy resources. So one of the first objectives is to be able to dispatch the microgrid DERs, distributed energy resources, which can include renewable systems such as solar, wind, also look at energy storage, and conventional generation such as diesel generators and so on. One of the key components is be able to manage the grid-connected system as well as the islanding transition. One of the definitions of a microgrid is that the microgrid can operate on both grid-connected and islanded. Another condition or objective is to optimize the distributed energy resource utilization. That means that you want to use as much renewables as possible in the microgrid. You want to minimize operation costs, so it needs to have an understanding of the cost of generation, different types of generation, and energy costs from the utility. Also, demand management is very important. If you island a microgrid, typically the energy resources in a microgrid are not sufficient typically to maintain the demand on the system. So the microgrid controller needs to be able to balance the generation and load demand in that microgrid. Also to provide an operator interface, so the microgrid can be controlled manually when desired, and be able to generate reports of operations and receive set points from the distributed energy resource management systems. The ETAP microgrid and power plant controller are based on a digital twin technology. The digital twin allows us to perform design and feasibility studies, be able to go to every single component within the microgrid and be able to design it, be able to evaluate it, be able to test it. As a user, we need to understand the capabilities of each of these components in the microgrid or the power plant. Also, we need to look at renewables, as I mentioned, solar, wind, hydro, and also look at the energy storage size, like battery sizing. It's important to be able to do battery sizing. This is all performed within the ETAP digital twin model. Also sizing the capacitors and the static compensators, perform evaluation and testing, and also look at the optimal settings. As shown here, EPPC main execution rate is few seconds depending on the number of tags, supported functions, and hardware selection, while the gateway PLC execution rate is in milliseconds. Functions implemented within the gateway PLC is also managed through the ETAP power plant controller. The combination of ETAP power plant controller and gateway with the PLC functionality allows us to implement a model-driven and software-based power plant control, realize digital twin, and achieve agile development process while implementing required high-speed secondary functions in the gateway PLC. This architecture also allows us to easily handle hybrid plants, including different types of renewables, energy storage, and reactive power. In case of a large hybrid plant, each plant can be controlled by a PPC, while the entire hybrid plant is controlled by a master power plant controller. Energy storage and reactive sources can be controlled by one or more power plant controllers. In this architecture, each power plant is responsible to meet master controller commands by dispatching assets under its control. Master PPC is mainly responsible to meet TSO commands by determining and dispatching commands to each plant controller. The ETAP power plant controller offers several control functionalities that are essential to basic and hybrid renewable power plant applications. Active power can be limited or controlled at the point of interconnection based on operator TSO schedule commands. Rule-based or optimal dispatch can be executed to minimize import power costs, limit exporter power to the grid, take benefit of price arbitrage, maximize peak shaving, and more. Reactive power control functions allow QV power factor, QV control at the point of interconnection. Ramp rate control are applicable to both active and reactive power controls. Soft start can be applied to a plant collector. Plant islanding to a seamlessly island plant at the plant time by preparing plant resources as well as controlling POI, power point of interconnection, active and reactive power. Islanded management and control, manage and control plant assets in an islanded mode of operation. Reconnect to grid, detect a stable grid availability, and initiate synchro checking at point of interconnection and monitor status of reconnection. Similar to the ePPC, the ETAP microgrid controllers can perform the listed functions. Optimal dispatch. Actually look at the energy cost, generation cost, and dispatch according to these parameters. It can also be configured to be rule-based dispatch, so for example, manage demand control, perform load sharing. Now the intelligent load sharing is optimal, so the system decides how much load needs to be shed or curtailed, and determines the best combination of loads to shed within milliseconds. So the response time, we're talking about between 10 to 40 milliseconds depending on the size of the system and the communication protocols available. There's also active power rate control, renewable smoothing, reactive power control, islanding control, and also black start. In some microgrids, they island, but they don't automatically start its energy sources. So for example, you can have a diesel backup generator in which it's required to do a black start for them. So now let's look at the ETAP 21 Intelligent Controller Enhancements. The controllers has been handled in the past years as projects, and the element and functionality was hidden from the users. Now in ETAP 21, we have decided to provide you access to it. In the design side, we have added the controller component, and that can be defined as a microgrid or power plant controller. It has a built-in digital twin model to perform design and software in the loop simulations in a quasi-dynamic mode through the time domain load flow and dynamic simulations through the transient stability module. Main difference is the time step and the validation you want to perform. So here, let's look at ETAP 21, and we can see that we can drag a component, a microgrid controller, just like we do with any other object in ETAP. We can look at the properties of this component and actually make the interconnections of all the different components that it will either monitor or control. So you can hear here we have many inverters for the PV arrays, and we can see that which ones are being monitored and controlled. We can also go to the device settings. All the device settings will be visible, time delays, any set points, anything that is related to the power plant controller or microgrid controller. We can see, for example, the capability curves of the plant. So all of that information is entered to the controller component. Once the controller is modeled, we can create different scenarios. These scenarios will be executed. So for example, right now I'm looking at a quasi-dynamic simulation to the time domain load flow. The time domain load flow connects to the digital twin of the microgrid controller. We look at the results on the one-line diagram, as well as, which is easier to look at anyways, is to go through the trends, the plots. So we can go and select, for example, the point of interconnection. We can look at, for example, total active and reactive power control, and we see the results. For example, in this example, we're actually looking at the response of the system, which includes all the generation based on transmission system operator commands that's sent to the controller. So here I'm going to show you another simulation. In this particular case, we're going to look at a transient dynamic simulation. So I select the transient stability module and I select to execute. So in this particular case, we're actually looking at the over-frequency response of the system, including the microgrid controller. So let's look at the generation response based on this. For example, we can see here that the system goes unstable based on this over-frequency condition. So on the operate, which is the actual controller system, we have done several enhancements. First of all, we have improved the quick deployment to the hardware. So once you have performed your simulations, your software in the loop simulations within the design package of ETAP, by getting the operation side of the system, you'll be able to download the same logic, the same digital twin model that you use to do your validations into the hardware. In ETAP 21, we provide you with an interface with the different communication protocols that will allow you to communicate to the controller and actually perform the same studies that you perform during your simulation, but with the actual hardware. This will allow you to actually best test the response time and also make sure that the right digital twin has been loaded into your hardware. Once that is loaded, then that goes into the final controller, and that controller can be implemented in the system. So let's look at how difficult, I should say, how easy it is to deploy. So we go into the controller, we double click on it, we go to the associated devices and we hit deploy. And by clicking deploy, now we generated the files and they're loaded into the controller itself. Also, we have improved the interface to the controller. So you have basically an IP connection to the controller. So you type the IP in a network that you have access to the controller. Here we can find product information. We can look at the settings that have been loaded into the controller. For example, we can look at the rule-based dispatch set points here. You have records, for example, and these records will be events, reports, and waveforms. In this case, sorry, I don't have anything loaded. And then we can also look at different versions that have been loaded, when they were loaded, which user actually loaded the logic. From here we can actually request an update. We can restart the controller. We can stop the controller. We can perform a cleanup, which means reset all the settings of the controller. Obviously, you have to have the right access levels to be able to do that. So with ETAP, if you want to, for example, enhance different functions of the controller, or you want to model in a specific controller, you'll be able to contact our service group, and we'll provide services to develop the new control functions, enhance or tune the existing functions, test and validate them, be able to perform, generate a digital twin for the controller, and also be able to perform the software in the loop and hardware in the loop testing if required. ETAP can provide these services commercially, also available for universities as well. Just as a quick reminder, the system has a complete interoperability in mind. So the controller has an Ethernet IP connection and connects through a gateway. We can connect to any serial device and any digital input, digital output, analog inputs. We can also do it through communications through DMP3, Modbus, IEC61850, IEC104. So the interoperability is covered. So in summary, with ETAP 21, you'll be able to configure and simulate and validate using the digital twin of your system, your power plant or microgrid. You will be able to also have the digital twin of the power plant controller to do that. You'll be able to deploy the digital twin into the actual controllers, and we are here through our engineering services to help you develop and debug the system. So thank you very much for your attention, and if you have any questions, feel free to contact us. Thank you.